I guess we're on part 3 now,
Yeah.
so there's not much need for me to say anything to introduce it. So hi, Tim, go ahead.
Thank you so much, Perry. Yeah. So welcome, folks, to part 3, which was unplanned. We're really covering for a cancelled seminar, so instead of cancelling the session altogether, Perry and I, thought that it may not be a bad idea to have a part 3 and discuss further. So I apologize at the beginning that some of the slides will be repeated from parts 1 and 2, just to have a coherent story altogether today. And I'd like to start at the beginning by recalling this early debate and early schism in the community at the beginning of aviation. As we all know, when the Wright brothers made history in 1903, there was no guiding principles, no theory to answer even the simplest questions in aeronautics, like how much lift a wing can produce, for example. So it's a fair assumption to assert that almost all airplanes built at the time were built by trial and error. And the story becomes a bit more interesting when you recall the political tension in Europe at the time. So for example, when Louis Blériot made the first cross-channel flight from France to England, newspapers in England came the next day: Britain is no longer an island, the nation's basic line of defense is breached, the channel is no longer a moat that makes the island impregnable fortress. So you can imagine that the emergence of this new machine that could change the course of a war, an impending war, this put some pressure on the engineers and scholars of the two competing nations at the time. So as George Bryan, who developed stability derivatives, he said, the Germans are probably putting their best brains into improving their aeroplanes. And as Greenhill described it, it's a mathematical war. So right before, during, and after World War I, there was a parallel mathematical war between England and Germany to develop two theories, one for lift and one for stability. Of course, today we're concerned more with lift. Out of this competition came two theories of lift, one in England and one in Germany. The one in England was the discontinuity theory of lift by Lord Rayleigh in Cambridge, building on the concepts of Kirchhoff and Helmholtz, basically the free streamline theory, if you have seen Schurbager's work. In Germany, there was the circulation theory of lift, 2D by Kutte, 3D by Prandtl. And the interesting point is that this circulation theory of lift started in England first by Frederick Lanchester. Lanchester was a practical engineer, did not belong to this elite group of Cambridge mathematical physicists. They rejected his theory. And on the other hand, the Germans, they accepted the theory. They actually invited him to Göttingen, where he had dinner with Prandtl, and they took these ideas and built upon them to develop the successful theory of aerodynamics. Now we're more than 100 years later after this debate or this competition. So I can spoil the movie for you. This is the circulation theory of lift as we know. It asserts that the flow over the wing is an irrotational and ideal flow with circulation, and this circulation dictates the lift. This is the movie I was going to spoil. This is the variation of the lift coefficient with the angle of attack. Three theories. The black is the circulation theory of lift that we teach to our undergrads, 2 pi alpha kind of thing. Blue is the discontinuity theory of lift by Lord Rayleigh. And red is the Newtonian theory that we discussed in part 1, the sine square law kind of thing. As you can see, both the discontinuity theory and the Newtonian theory, they significantly underpredict the lift force. In fact, if they were to be true, aviation may not be possible. Probably the question is, why did the British school reject the circulation theory of lift? Right? That's a legitimate question. And we discussed some of these arguments last time. I'm going to repeat some of them. I apologize for that, just for coherence of the story. Here is Jai Taylor is complaining. Mr. Lanchester loses the possibility of generating the motion from a state of rest by movement of the solid. And this is the most important criticism. Let me explain it. If you have your airfoil, this is the point. From rest. That's the main issue. From rest. You cannot generate it from rest. So from rest, if you have your airfoil at rest, then if you take any circulation around the airfoil, gamma is 0, of course. Now let the airfoil move. If your flow is indeed irrotational, we have Kelvin circulation theorem. Gamma is conserved. So you cannot generate gamma. Gamma will remain 0, and you will not be able to generate lift. That was the main criticism until nowadays. I mean, many people, not everyone believes that, but many people. So here is J. Taylor is adding, in searching for an explanation of the forces which act on solids moving through fluids, it is useless to confine one's attention to irrotational motion. And he was so precise to say irrotational, he didn't say inviscid. But the implication is that, you know, in a purely inviscid fluid, you will not be able to generate vorticity anyway, so you will remain irrotational, and if you remain irrotational, you will not be able to generate lift. This becomes clear when you look at other statements of the same school. Bairstow, one of the most, you know, prominent members in the Cambridge School of Mathematical Physics at the time, his book Applied Aerodynamics. It appears to be fundamentally impossible to represent the motion of a real fluid accurately by any theory relating to an inviscid fluid. Cowley and Levy, the failure of the various treatments of the problem is evidently due to the supposition that the fluid is perfect. You can see that they are really bothered by the assumption that the fluid is inviscid or perfect. And they invoked a viscous theory that will clarify at one stroke the whole problem of aerodynamics, right? But if these seem to be very plausible objections and arguments. If this is the case, why did the German accept the theory? I mean, were they weak in aerodynamics and fluid mechanics? I mean, obviously they were aware of these arguments, these concepts in fluid mechanics. Why did they accept? In fact, the two schools, they had very different perspectives on many points. For example, the concept of ideal fluid to the Cambridge School, this is just fictitious. There is nothing called ideal fluid. In the words of Professor Melville Jones, a later professor at Cambridge, it was regarded purely as an exercise for the amusement of students. You know, it's a material for prelim exam, like we use 230A here for prelim exam, but it's not for adult and serious research. On the other hand, the Germans, they view the ideal fluid as a good approximation of the average flow at a high Reynolds number. This statement, in fact, was by von Mises. Interestingly, we will see later in the talk today that probably 100 years later, Greg Eyink is making a very similar statement. Just remember this statement. To the British school, lift is purely viscous. Don't waste your time. Go and solve Navier-Stokes equation, period. And we know now that this was not a very wise decision because we're 100 years after and we cannot routinely solve Navier-Stokes equation on an actual airplane, actual wing. To the German school, ideal fluid theory provides a reasonable estimate of the lift force. So I'll give you a concrete example, demonstration on how they viewed things different, actually related to D'Alembert paradox, which is, the inability of an ideal fluid to produce drag, right? So here is Lamb from the Cambridge School. He's saying, this theory cannot tell us why an aeroplane needs power for its propulsion, right? So he's mocking up. I mean, guys, you're using a fictitious concept, so it's not surprising that this fictitious concept is giving you paradoxical results. I mean, if it's true, we should not need engines for our airplanes, right? So he's making fun of the theory. So let's see how the Germans interpreted this zero drag results. Very interesting. 1911, Foreman, a student of Prandtl, he made this experiment. We know from undergrad, or at least 230A, that we can come up with sources and singularities to construct shapes, right? And the theory gives us everything for these shapes: velocity distribution, pressure distribution, and it will result in zero drag. Yeah, we understand. So Foreman constructed 6 of these mathematical shapes, and he built them actually and put them in the wind tunnel to compare. He knows that the theory will give zero drag, but he was interested in the pressure distribution itself. And he found that the pressure distribution by the theory matches actually reasonably well the experiment. Not only that, for rounded nose, if you have a rounded nose and slender body, it's small thickness, and those shapes that are relevant for aeronautics and aviation, found that these shapes, they enjoy very small drag. And almost all of this drag is due to friction, because he has access to the pressure distribution, so he can get the pressure drag, So let's see how Prandtl himself interpreted this result. So in 1923, NACA report by Prandtl, he wrote the following: the theoretical theorem that in the ideal fluid, the resistance is 0, receives in this a brilliant confirmation by experiment. So one is viewing it as a fictitious, Prandtl is viewing it, this is a brilliant confirmation by experiment. This is so practical. Why is that? He's basically saying, first of all, this theory ignores friction from the get-go. So don't talk to me, about friction. So let's see the other component of drag. The other component of drag in these shapes is negligibly small. So a 0 is a very good approximation of a negligibly small number. That was his mindset.
That was a wind tunnel experiment?
Yes, yes, yes.
And the NASA report, I assume, is a translation from the German.
Yes, exactly, yeah.
They didn't pay you very much for that.
Yeah, Frankel, he did not speak English. Max Monk, yeah, go ahead, Brian. You want to say something? No, he actually didn't speak English. No, he didn't speak. So, we can talk about this later, but no, he did not speak English. Max Monk, one of his students, he had a very interesting paper, Annual Review Fluid Mechanics. The paper is looking back in his early aerodynamic research with Prandtl. And he wrote the following. The wind tunnel was asked whether the study of the motion of a perfect fluid was helpful for practical aerodynamics, right? And then he said, it answered with a loud yes. This was very great achievement of Prandtl, one for which he did not get enough credit. So you can see they saw the same mathematical and experimental fact, they interpret them differently, right? And this is not the only one. There is another one on the circulation and Kutta condition, but I don't want to go into this because it's related to our work. I don't want to make this about our work. So perhaps the question, if this is the case, and they have very different mindsets, so why at the end the Cambridge School accepted, at least partially, the circulation theory of lift, and now it's being taught at Cambridge itself? We discussed this in part one, right? There are several incidents. We discussed one of them, the confrontation in the International Air Congress in 1923 in London, particularly this morning session of June 27, 3 speakers. And I will not dwell much because we discussed in part one. I'll just mention the last paragraph by Lowe. His conclusion was, if you remember, in conclusion, it is desired to call attention to the fact that this fundamental physical theory was first stated by an English writer and then allowed to fall into complete neglect in the country of its origin, largely owing to the attitude taken up by some of Lanchester's fellow members of the Advisory Committee for Aeronautics. This was in front of the people from the Advisory Committee for Aeronautics, Bearistow and Glazebrook. So accusing them in front of their faces that you guys wasted a golden opportunity. We could have the leadership in this. It started already in our own land, and it's related to a critical machine like airplane at a critical time, like a time of war. Because of these serious allegations, they had to take it serious, put Prandtl's experiment under extreme Prandtl theory, under extreme experimental investigations. 2 main experiments were done. We discussed one here in part one by Brian and Williams, which triggered the debate between Taylor and Glauert. We discussed this. And at the end, Taylor conceded. And why? Mainly because of this picture. If you remember, this is basically the experimental grid. There are numbers in the middle of these squares. These numbers represent the circulation of each square. And you can see that these numbers are all almost zeros. So there is no vorticity in almost the entire domain. The flow is indeed irrotational, in addition to the fact that all gammas around airfoil are the same, independent of contour, satisfying Rho gamma. So all what Prandtl theory was predicting came out to be correct. So they had to at least partially concede and give them credit. As we discussed in 1926, they acknowledged Lanchester was right. They invited him to give the Wright Memorial Lecture and received the gold medal from the Royal Aeronautical Society. In the very next year, Prandtl received a similar honor. And we discussed, around 1930, Taylor sent him a letter saying, you deserve Nobel Prize in Physics, right? But they were not comfortable, or fully comfortable, or fully convinced. And we also touched upon this, and I'm going to repeat it, I'm sorry. I like this paragraph actually by Bearistow in his lecture, when he said, aerodynamic theory is now rather like the physical theory of flight. Physicists use electron theory on Mondays, Wednesdays, and Fridays, and the wave theory on alternate days. Both have uses, but reconciliation of the 2 ideas has not yet been achieved, so it is in aeronautics. In our experimental work, we assume that viscosity is an essential property of air. The practically useful theory of Prandtl comes from considering air as frictionless or inviscid. They were not, so the theory is working, fine, give you the credit, but we're not comfortable, we're not fully convinced. And why is that? So the theory is based on, seem to be plausible concepts in fluid mechanics, and it's working, in experimental world. So why they are not accepting it? Because the theory gives them the final value of circulation and lift. It does not show how the lift and circulation develop from rest. That's the main issue. How you generate circulation from rest in a purely inviscid fluid? And if you need viscosity to generate it, how come its role come to disappear at the end? So they were not comfortable. So in David Bloor commentary, he said, at the time, British experts acknowledged that many questions had now been answered, but not this one. How lift and circulation is developed from rest. You need viscosity, you need boundary layer, to generate vorticity, and circulation is a global measure of vorticity. So on the role of boundary layer, you can see Professor Southwell, Cambridge, he wrote this, very interesting. He said, the conditions in this layer are the ultimate mystery of aerodynamics. Somehow or other, in a film of air whose thickness is measured in thousandths of an inch, that circulation is generated, which we have just seen to be the essential ingredient of air. So he's basically saying, as many of us believe, right, everything develops in the boundary layer. It is the boundary layer that, drives the whole flow. It's not the other way around. The German school, they're saying it's the other way around. The boundary layer is just reacting to the outer flow field. He's saying, no, that's the main meat. And in fact, you will see this pretty common nowadays in the wake of when we developed the variational theory of lift. We had one conclusion that unleashed many criticisms. What that conclusion? That the Kutter condition doesn't seem to be viscous. This just single statement, many people did not like it. Professor Liu, for example, he wrote a couple of papers on this. He doesn't like the fact that the Kutter condition is viscous. So he wrote, the generation of the airfoil circulation associated with the starting vortex is a viscous flow process, So it's matching the Cambridge School of Mathematical Physics, matching this line of thought. You know what's the irony is? In 2019, 6 years ago, I had a JFM paper myself, and I wrote an almost exactly similar statement to this, that the development of circulation and lift is essentially a viscous process. But I converted over the years, and during this transition, it was really illuminating journey for me. So let me tell you how I think of it. So yes, please.
This is not our Professor Liu, just to clarify.
No, I'm sorry. Yeah. No, he's not.
Because he's not here.
No, Fang Lu is my friend.
I don't want people to have the impression that you're somehow saying something.
No, yeah.
He's not here to defend.
Yeah, thank you. This is not Fang Lu, of course. No. It's somewhere in Michigan. Don't remember now. That's a good catch, by the way. Okay. So there is something in the logic and philosophy of science, particularly causal inference, something called the method of difference, or sequential elimination, if you want to say. So what's that? If we have a box, a heavy box that is full of balls, and the claim is there is a particular ball that is responsible for the heaviness of the box. How to test this hypothesis? It's so easy. Remove the ball, check the box if it's still heavy or not, right? That's easy. So if the claim is, well, viscosity is an essential ingredient for lift generation and drag and circulation and all these kind of interesting phenomena, well, remove viscosity and see what happens. This is in essence what Professor Peter Tabarek is doing in his lab. He's experimenting with crazy fluids, superfluids, which have zero viscosity basically. But we can do this with simulation also. And when we do it with simulation, this is what we get. So this is Hirsch's book, CFD, Volume 2, Section 19.4. It appeared that computations based on the Euler equations and which did not implement any form of the Kutter condition still produced accurate results of circulation. This has been confirmed since then by many computations in 2-dimensional as well as 3-dimensional airfoils and wings. And he added, this remarkable result implies the existence of some mechanism, because it's not viscosity now, there must be some mechanism which reproduces and simulates the essential physical phenomena leading to the generation of circulation and lift. And this was some wave in the 80s, and in fact, it served industry very well, the aeronautical engineering industry. They used to do Euler simulations mostly until the RANs became mature. And then another wave of simulation came by Hoffman and Johnson. Again, they are writing. We find by computational solution of the Euler equations with slip boundary conditions that the potential solution develops into a turbulent solution with substantial drag and lift. We thus obtain, without any presence of viscous boundary layers, substantial drag and lift. They add, in particular, we show in these references that drag and lift of a car or airplane can be accurately predicted by computing turbulent solutions of the Euler equations with slip boundary conditions without resolving thin boundary layers. So, to me, I mean, or at least from a pure logical perspective, this should have been the end of the debate. We removed the ball, the box remained heavy, we removed viscosity, we still got lift and drag, right? But here is the last straw. So the response from the viscous school, hypothetically, was something, oh, that's interesting. How you guys simulate Euler? Because when we try to simulate Euler, it blows up. The response was something like, oh, we had to add numerical dissipation to the numerical algorithm to stabilize the numerical algorithm. So the response was, aha, now it's artificial viscosity. This numerical dissipation plays the role of artificial. You see, you need viscosity somehow. So let me summarize the debate to you. So D'Alembert paradox asserts that irrotational flows can have forces, while the other school can respond that, well, with an irrotational circulation, we can have lift just fine. Yes, but you will not be able to explain how this circulation is generated from rest. That's the issue, in an ideal fluid without viscosity. Because circulation is the measure of vorticity inside the boundary layer, and you'll not be able to generate fresh vorticity from rest without viscosity. That was the main issue. You really need viscosity, right? The natural response was, well, but when we simulate Euler, we got lift and drag, but we had to add numerical dissipation. So that was the last straw. See, you need dissipation, you need viscosity, right? But in these simulations, we don't have boundary layer. We don't enforce the no-slip boundary condition, which is really a critical thing, right? Yes?
The answer should be you need dissipation, whether it comes from viscosity or something else.
Yes, so I think, I don't know if you agree with this.
That would be more general.
I think if you, I don't know if you agree with this or not, but so this is just a hypothetical thing. Yeah, still you shouldn't have any dissipation, because at the time Euler is known to be conservative. So any dissipation is extraneous to Euler, is artificial. So now you're playing around. This is not a purely Euler simulation. You need viscosity. So, and to this argument, there was no proper response. I mean, there is what you can say. Euler is supposed to be conservative. It seems that this dissipation is extraneous to Euler.
But my point is that the artificial numerical viscosity could be replacing some other kind of dissipation besides viscous dissipation.
So you're here. You're with those guys or no?
Well,
I mean, I totally
agree with everybody.
By the way, I totally agree with this statement first. I totally agree with this statement.
Have you read Srinivasan's papers?
I'm sorry?
Have you read Srinivasan's paper on it?
Which one? Yeah, I mean, not all of them, but yes.
I haven't read all his papers, but what he told me is that he started off believing that superfluids
Have dissipation.
could represent potential flow because they didn't have viscous dissipation. What he learned was they had vorticity generation and another kind of dissipation via sound. And his conclusion is that the important thing is dissipation.
Exactly.
Whether it's viscous or something else.
Agreed.
And I think, I bring it up because I think that's the best way to frame it.
I agree.
In different physical situations, you might have different dissipation, but I think for lift, you need dissipation.
Yes, for lift and pressure drag. Yes, exactly. And yeah, I completely agree. I'm aware of this line of work. I'm not sure about the particular paper.
In subsonic flow is true.
Sorry?
In subsonic flow is true. In
Yeah.
supersonic you don't need.
What, if you have shock waves, you mean?
Yeah.
Well, it's another kind, well.
Yeah, the shock wave will give you, we will talk
No,
about this
no,
in a touch
You're
upon it.
agreeing with me. You need some other kind of dissipation.
Yeah, okay.
We-
My point.
Nobody disagreed, Bill.
But not viscosity. Well, yeah, I don't
It
know.
doesn't have
It's
to
not
be
viscosity, yeah.
It's not
Usually it is, but.
Now we're going back. So it's so that was the case, and interestingly, the recent development in the math community, they came and provide some arguments that help these poor guys to respond or at least to reconcile with the viscous school. And it was not a single, incident. It was really a long journey that probably started very early on with the work of Helmholtz in the late 1800s. So he started by acknowledging the large deviations between reality and the results coming from theoretical analysis, of course, of Euler, all right? And he wrote, one would like to suspect that the root cause of that situation lies in the internal viscosity of the fluid. Although there are all sorts of strange and jump-like irregularities that cannot be explained by viscosity. Fine, if it's not explained by viscosity, how are you going to explain it then? So he's saying, in the equations of hydrodynamics, the velocities and pressure are treated as continuous functions of the coordinates. On the other hand, there is nothing in the nature of a drop-forming fluid when we consider it not subject to viscosity for saying that two fluid layers that lie next to each other cannot slide past each other with finite velocities. So he's basically saying that these physical flow fields that we observe in reality, when we view them from the lenses of Euler, they can be discontinuous. All right, they can slide with respect to each other, basically a jump in the tangential velocity, a vortex sheet kind of thing, right? And if this is the case, then our equations don't seem to be a good model, kinda, or how there is no mathematical framework to understand these, because our equations, they assume that these functions are continuous function of the coordinates. In fact, they assume that it be differentiable, right? We have the derivative in the equation. So, in fact, Batchelor is saying something similar. If you go and open section 5.3, Batchelor, let's read together. He's saying, it's not quite sufficient to assert that if omega 0 initially, then omega will remain 0. That's of course, we're talking about ideal. This is the main issue, right? That's the whole thing, the whole business about this, right? If you start with 0 omega, will remain 0 omega in the absence of viscosity. So he's saying it's not sufficient to have this conclusion. As Stokes pointed out, a more complete argument of the following kind is needed. And this is just in Batchelor. Go and open it, you'll find this. So he's saying the norm of vorticity at any time is bounded by the norm of vorticity at the initial time with some exponential. So if this is finite, then yes. And if this is 0, this will remain 0. What is k? K is the greatest possible value of this multiplication. Omega hat here is the direction of vorticity vector. And this is the velocity gradient, all right? So he's saying, Batchelor, I'm quoting, if now we can put the initial vorticity to 0, it follows that the vorticity at any time 0 also, provided k is finite. There is a similar restriction on the magnitude of velocity gradients in the proof of persistence of irrotationality. So this section was for Kelvin circulation, the conservation of circulation, right? So he's saying, no, you cannot conclude that ideal fluid will not generate vorticity and will conserve circulation unless you have a finite velocity gradient. If you have a finite velocity gradient, yes, we agree with you. So that was the main thing. So it's, if you, again, recalling that in Helmholtz, he said, realistic flows, Euler flows, they should be discontinuous. If they are discontinuous, the derivative is not even defined. So here Batchelor is saying, if the derivative is not bound, if you cannot guarantee that the derivative is bounded, then these theorems no longer hold. Here is the question at the early debate, or even around this time, it was not that well known. If the gradient is not bounded or is not even defined, how are you going to make sense of the equation itself? The equation has derivative, right? So this leads to the concept of weak solution. I showed part of this slide last time. I apologize. I think we have to see it again, and probably with more details this time. So again, you recall this example, very simple example, cubic equation in 1D. And if I ask you how many solutions do we have here, if you are in the middle school, or even if you're adult, but before 1500s, before we learn about complex numbers, then you're going to say with full confidence that this equation has only one solution, right? But if you're an adult living in the modern time, learn about complex numbers, we know that this has 3 solutions. The main lesson is once you open the space of solutions over which you're doing your search for solutions, new solutions may emerge, all right? And some of these may be physical. The same applies. The same applies to what did you say, Ben?
I like your example.
Oh, thank you. I'm flattered. Thank you so much. So the same applies to ODEs and PDEs. If you have a differential equation like this, and if you're before 1940s, where we can make sense of solutions of this equation only when we talk about smooth functions. Why? Because what does it mean, a solution for this equation? Solution for this equation is a differentiable function, because I need the derivative here. So I need the derivative defined at everywhere, such that when I evaluate it at some y, multiplied by y, evaluate the function at the same y, multiplied by sine y, they cancel each other, right? That's the definition of a solution. And this equality happened for all y. So I need the function to be differentiable for all y, be smooth. Well, if I'm looking for a discontinuous solution, how can I make sense of a solution here? I will not be able to evaluate this term to begin with, right? That's the issue. So here comes the role of Schwartz theory of generalized functions and the theory of distributions developed mainly in the 40s and afterwards. So basically, they say the following. Well, okay, let's see. We're going to multiply this equation by some test function, smooth function phi, and integrate over the domain. What was your main issue in this equation? Well, it was the derivative. Fine, I'm going to get rid of the derivative by doing by parts. Because when you do by parts, this derivative is transferred to the other functions, and now your function u doesn't have derivative anymore. But you pick up a boundary term, well, you kill it by assuming that phi vanishes on the boundary. And now you have this equation, boxed equation. So we're going to define u is a weak solution of this equation if it satisfies this boxed equation for all smooth functions that vanish on the boundary. All right? And now in this new form, which is basically the integral form, and it's nothing fancy for us as fluid mechanicians, right? This is for this integral form, you don't have derivative. The function doesn't have to be differentiable. In fact, it doesn't have to be continuous. All right? So now if you go and apply these tools to Euler, this is just a nutshell, of course. There is whole courses in the math community about this and whole books. And if you go and apply this to Euler with this lenses of weak solutions, then all crazy things can happen. None of the conservation laws that we know about Euler, whether it's energy, conservation of circulation, vorticity, holds anymore. Anything can happen. So this is basically like, it's like Greg Ienk was saying, it may be less commonly appreciated that the singular or weak solutions of Euler are good candidates to describe turbulent flow in the asymptotic limit as unit number goes to infinity, as first conjectured by Unser. Remember, this is very similar to the statement by von Mises in the German school 100 years before. It's almost exactly the same, that ideal fluids are good candidate to describe the turbulent flows at very high Reynolds numbers. But now, of course, he is coming at it with a rigorous mathematical definition of what do you mean by these solutions in the lenses of weak solutions and so on and so on. And Sagar, as we mentioned last time, he was a Nobel laureate in chemistry who wrote one paper in fluid mechanics in which he wrote turbulent dissipation could take place without viscosity. This is what Professor Soriano was mentioning. In the absence of viscosity, the standard proof of the conservation of energy does not apply, because the velocity field does not remain differentiable. This is very similar in spirit to what Batchelor was saying. He was saying if you don't have bounded velocity gradient, you don't guarantee conservation of circulation. Here he's saying if your velocity field is not differentiable, you don't guarantee conservation of energy this time. All right? But Sagar provided more. He provided and he conjectured a threshold below which you no longer guaranteed conservation of energy. The threshold, as we discussed last time, is Hölder continuity with exponent 1/3. Hölder continuity, again, is a quantitative measure of continuity between C0, the continuity we know, and C1, the differentiability or continuously differentiable. I give this example, and I think it's needed again. This is the purple function is x squared, so it's differentiable smooth everywhere. The yellow is absolute value of x, so it has a kink here. So it's not differentiable here, but the derivative, whenever it's defined, is bounded everywhere. So this is, we call it Lipschitz. It's Hölder continuous with exponent 1. Now you look at square root of x. This is the red function. It's also not differentiable here, but you cannot bound the derivative. The derivative is not bounded, all right? The blue function is with exponent 1/4, and so on. So the limit, the brilliant limit by Onsager was somewhere between the blue and red, is 1/3, x to the 1/3, basically. And it remained a conjecture for 70 years. Recently, Issett made a very rigorous mathematical proof of Onsager's conjecture. He constructed an analytical solution of pure Euler, that is dissipative. It dissipates energy. It does not conserve energy with absolutely zero viscosity, which is very interesting, frankly speaking. Let's get this. And Greg Eink also established a similar threshold on Kelvin circulation theory. From Bachelor, we already know that if the velocity gradient is not bounded, Kelvin circulation theory may not hold. Here, Eink is providing you with the threshold. It's 1/2. In a more recent paper by Eink, he wrote, the drag on the body in the infinite units number limit can be computed entirely from the limiting weak Euler solution without the need to resolve small viscous length scale at the wall. I think all this can be probably summarized by, under very modest assumptions, the viscous Navier-Stokes must tend in the limit to a weak solution of the incompressible Euler. So basically, once we open the space of Euler solutions to include weak solutions, many things can happen. Weak Euler solutions are very rich. They generate drag and lift. They do not necessarily conserve circulation or energy. They can generate turbulent dissipation. They can do many interesting stuff. They are rich enough to be candidates as limit of Navier-Stokes equation. All right? Now, how is this related to the old debate or the lingering debate on the artificial viscosity, numerical dissipation? We know that when we simulate Navier-Stokes with a relatively large, or actually a large mesh, much larger than Kolmogorov length scale, then we cannot simulate Navier-Stokes as is, and we have to add subgrid scale model for the Reno stress, right? And as we emphasized last time, I like to emphasize again that this has nothing to do with the molecular viscosity. This is due to the filtration of the nonlinear term, right? So one of the standard models, or one of the common models for the Reno stress is the eddy viscosity. There is, again, this issue. The eddy viscosity, right? And perhaps the name is justifiable, as Professor Ghabashi told us last time about the history of the name. But when you view it from the perspective of this 100-year-old debate, it's really confusing and misleading, because this term has nothing to do with molecular viscosity, right? It's actually due to the nonlinear term. So indeed, the action of the eddy viscosity is not viscous. This is inertial. This is to begin with. But if it has nothing to do with viscosity, and it's really due to the nonlinear term, and the nonlinear term exists in Euler also. So this means that when we simulate Euler, why don't we use an eddy viscosity model with Euler simulation, right? Because the same term exists there. The line of thought at the time, maybe, 20, 30 years ago, was Euler is supposed to be conservative. You should not add dissipation to Euler. When you design codes for Euler, they should be conservative codes. We understand that you need to add numerical dissipation to stabilize your numerical algorithm, but from physical perspective, Euler should be conservative. You should not add dissipation. Now we know more, right? Now we know from Onsager's conjecture and these solutions from the math community that Euler itself intrinsically has dissipation. The concept of dissipation is not extraneous to Euler, particularly if we are interested to capture realistic flows. Because these realistic flows, according to Helmholtz, they are expected to be discontinuous. So discontinuous solutions are not conservative. They are dissipative. They can be dissipative. So if this is the case, if you really want to do proper simulation of Euler, you should have a subgrid scale model, very similar to what you're doing with Navier-Stokes, because of the nonlinear term. It exists in both equations, and dissipation exists in both equations. Yes, viscosity provides an additional dissipation, but this is not the point here. So now if you look at it from the point of view of implicit LES, we know that you can replace a subgrid scale model with a numerical dissipation of your numerical algorithm. And there is debate in the community which is better, to have a subgrid scale model with a conservative numerical scheme versus a dissipative numerical scheme without a subgrid scale model. But there is some equivalence, right? This is not my point here. So if you look at it now, let's recap. If we want to do proper simulation of Euler in the light of these results, we need to add a subgrid scale model. Alternatively, we need to add numerical dissipation from the perspective of implicit LES. This is exactly what the successful simulations of Euler were doing, which we called before artificial viscosity. So indeed, artificial viscosity is neither artificial nor viscous. It has nothing to do with viscosity because it's not related to here. It's actually a model of the subgrid scale model, right? Which is related to the nonlinear term. And it's not artificial because dissipation is not artificial to Euler. It's intrinsic to Euler, all right? So there are a couple of slides that I really wish to give to talk about. Maybe there is more to this. Yeah, there is more to this. We showed this last time, which is interesting actually. This is the energy spectrum. This is wave number, right? Which is the reciprocal of the length scale. So large length scale will come here to the left, right? This is the inertial range, viscous dissipation, Kolmogorov length scale. So for Navier-Stokes, we have a clear length scale below which we don't need to add dissipation ourselves. Viscosity will take care of it, right? For Euler, there is no such length scale. The leak in energy is continuous. It continues indefinitely. So if you do it at any finite size, you will have to add dissipation yourself, all right? Particularly if you're doing it here, which is much larger than the Kolmogorov length scale. Even if you're doing it for Navier-Stokes, this is the resolvable range. Viscosity is not giving you anything in terms of dissipation here. It's not giving you anything. And this is why in a recent paper by Finn, very interesting paper by the way, very interesting. For a finite spatial resolution at very high Reynolds number, molecular dissipation through the viscous term is impossible because you don't see it there. Because the small scales relevant for molecular dissipation are not resolvable. Hence, look at this. The Euler equations are actually the mathematical model seen by the numerical discretization scheme. So viscosity is not, even if you're doing Navier-Stokes on a large grid like LES or RANS, of course, this will not give you any dissipation. The viscosity, so it's as if you think you're solving Navier-Stokes, you're actually solving Euler from the perspective of dissipation. So let's go to the couple of slides that I did not show last time. I did not have time to show, and I think they are interesting in some sense. So I want to go back to this debate, early debate, between the British school and the German school. Now equipped with these mathematical tools of weak solutions, on Sagar's conjecture and dissipation anomaly. We know that when the British acknowledged the contribution of the circulation theory, they invited, in 1926, they invited Lanchester to give the Wright Memorial Lecture and receive the gold medal from the Royal Aeronautical Society. And in the very next year, they invited Prandtl to receive a similar honor. Prandtl was very smart to devote his lecture to address the concerns of the British school. What was the main concern? The main concern is that how circulation, gamma, and vorticity can generate in an ideal fluid from rest, right? That's without contradicting Kelvin's theorem, circulation theorem. That was their main concern, and it's still a concern to people nowadays, right? We see papers are talking about this. So Prandtl titled the paper, The Generation of Vortices in Fluids of Small Viscosity. Back to Professor Sirignano's comment about whether he spoke English or not. He did not speak English. He wrote this in German, and it is Major Law. Do you remember Major Law? He was criticizing the community. He was the one who translated it into English. The paper is available online. You can go and read it. It's I consider it one of the most important papers, because look at the occasion, look at the debate, it's an important incident. So in this paper, he tried to explain to the British community how circulation can develop in an inviscid fluid, zero viscosity. And then he moved to the next section, how the picture will look different if we have a fluid with small but non-zero viscosity. Okay? So he wrote, every confluence at sharp edges can, without contradicting Kelvin's theorem, give rise to a surface of vorticity, a vortex sheet. He's saying this is the picture. You know, he's talking about confluence. When they come and meet each other at the sharp edge, there can be some discontinuity. And this sheet of discontinuity has nothing to do with viscosity. It does not contradict Kelvin's theorem. Fine. And then he wrote, a discontinuous distribution of velocity is set up which effectively constitutes a sheet of intense vorticity. The surface of discontinuity then begins to roll up into a spiral. And the gamma dot, the rate of change of circulation over the airfoil, has nothing to do with viscosity. It just depends on the jump here. And you can show that mathematically very easy. Right? So this is the picture when you have zero viscosity. I think, in my own opinion, what Prandtl missed, because this was not available to him at the time, to say this is a perfectly legitimate weak solution of oil. And this concept was not available to him, so Prandtl could not speak this language. Then he moved to the next section, to explain how the picture will be different when you have small viscosity. So he said, we can now see that layers of very small but finite thickness play the same part which we have already ascribed in the previous section to surfaces of confluence. We now have layers of vorticity instead of surfaces of vorticity. The picture is, instead of having this picture, we will have that picture. All what viscosity does is smears out this jump into a vertical layer of finite thickness. And then he adds, this difference affects but slightly the general behavior of the fluid, so that no serious error will be made if, in the case of flow behind sharp edges, viscosity is totally neglected. In both cases, you will have exactly the same rate of generation of circulation. Doesn't matter. And then he concluded, we thus get the unique characteristic that it is precisely these turbulent flows of low resistance around bodies which can be so closely represented by the theory of the perfect fluid. This is Prandtl himself, the father of modern aerodynamics, in one of the most interesting and important papers in his career. I personally believe that this should be known, by students and practitioners of aerodynamics and fluid mechanicians, because it's so important. And if it's widespread, I don't think that we will have too many people believing that lift and circulation absolutely needs viscosity. At least there's going to be some, some spectrum. So maybe a question here. I mean, this is just personal, thoughts. Why, this clear explanation did not make that great of impact on the British school? Yes, they accepted the theory, they gave him the gold medal, blah, blah, blah. But still, we don't see these writings in the common books. Or at least we don't see them, widespread in the community. So what was missing here, at least from the eyes of the British school? Again, this is just personal thought. I personally think that, this is a discontinuous solution. At the time, to make sense of a discontinuous solution as a perfectly legitimate mathematical solution was not available. I think if Prandtl, had written something like, this is a perfectly legitimate weak solution of Euler, it would have made impact on the British school, because they were a school of mathematical physics. They appreciated this language so much. But the concept was not available to him. This is one of the very interesting, moments in the history of science where the math came late in the game. Imagine a scenario. Imagine Einstein trying to develop general relativity, and there is no Riemannian geometry. There is no way to go. There is no way to go. He was so lucky, Einstein, that when he needed it, it was available. Remember, the Riemannian geometry, like many things in math, was not developed for a particular cause or a particular application. It was just developed, right? And then when Einstein needed it, it was available. indeed, the concept of weak solutions and Onsager's conjecture, dissipation anomaly, if it were available at the time, this is just fine. I mean, this is a weak solution, and we know that it's dissipative, does not conserve circulation. You know, I mean, Kelvin circulation theorem should not be invoked at all, and you know. So I think we have been struggling for 100 years because the math came late in the game, in my opinion. I'll skip this. Sure.
This picture you're drawing here, I mean, if you do like the classical, I'm going to calculate the lift from a Joukowsky transform, the solution doesn't look like that, right?
No, what you're describing is the steady, probably. This is unsteady.
So you have this in mind as like a transient.
Oh yeah, sure. Oh yeah, and this is a good question. Their concern was they acknowledged that the theory works for the steady case. And their question was, but you cannot explain the transient. That was the issue. And I personally received this criticism in the variational theory. We explained the steady. Of course, we mentioned nothing about unsteady, and people say, but you will never be able to explain the unsteady because it's purely viscous. It's the same story.
I mean, the startup wouldn't look precisely like this either, right?
It would look very similar to this, right? I mean, you have a this will create a this is a vortex sheet, right? So here it will look like this. This is precisely what they call the starting vortex.
Then you don't need Kuta condition at all.
That's an excellent point, Professor Mubashi. You don't need Kuta condition, but the issue is this jump could be arbitrary for Euler. You can have whatever strength. So you need something similar. They call it unsteady Kuta condition. But in my opinion, if you have a sharp edge, the Kuta condition, whether it's steady or unsteady, is perfectly legitimate because it's removing a singularity. So it's okay. If you made this smooth, then there is issue, and now there is no theory. We're trying hard to extend our theory to the unsteady. It's not easy. There's also Wagner. He developed an unsteady theory, but I'll skip this for the interest of time, and we'll go back to this debate, which was, remember, this school was could not respond to this argument of the artificial viscosity and dissipation. You still need some sort of viscosity. Now with these mathematical tools and with this understanding, I think they can respond. Basically, the realistic Euler flows, they can be discontinuous. So they have to be understood as weak solutions of Euler. And weak solutions can be dissipative. They can dissipate energy. They do not conserve energy. So the dissipation is not extraneous to Euler. If you want to do proper simulation of Euler, you have to include a subgrid scale model for the dissipation. And either a subgrid scale model, or alternatively, it's numerical dissipation in the algorithm in an implicit LES fashion. So that was exactly what that artificial viscosity is doing. So artificial viscosity is neither artificial nor viscous. Weak solutions of Euler are very rich. They can generate lift and drag and blah, blah. Peter, you had a question?
Can you actually calculate dissipation? Like in terms of your...
Yeah.
You said at the beginning,
You can.
How big of a motor do I need on my airplane?
You can, yeah.
Work?
Oh, yeah, you can. Oh, definitely. Yes. Oh, yeah, it gives you pressure drag. It doesn't give you the friction, right? So I'm not sure about the friction. I need to think about it. But at least, let's ignore the friction for now. It gives you pressure drag. So if you have a circular cylinder, for example, circular cylinder in the range of Reynolds number 10 to the 5, 2 to the 10 to the 5, this is the pressure drag is around 95%. It's not like an airfoil is very well designed, so pressure drag is very small, on the same order of magnitude as friction. But for other shapes, a car or a circular cylinder, pressure drag is super significant. You will get it. Yeah, that's the main point. In fact, there is the free streamline theory. Helmholtz developed the theory. Purely viscous, but with discontinuity. If you go and compute it and take the right parameters, you recover the drag coefficient perfectly fine. Pressure drag. Yeah.
But a problem with Euler weak solutions is that you have a wide range of arbitrariness
Yeah.
to attribute, in how you can attribute the dissipation and vorticity creation that occurs. in a layer. So I don't think the answer is in weak solutions.
So
Because you have to, it becomes weak Euler solutions plus some more physics.
so
You always need, if we're talking about lift, vorticity and dissipation.
So let's address one point at a time. From a purely mathematical perspective, not numerical, so I fully agree with your statement in the following sense. Weak solutions of Euler are not unique. And you need a selection criterion. And indeed, in my opinion, that's the $1 million question.
They're not complete.
No.
You have-
What do you
you
mean
have to
not
add
complete?
something.
What do you mean not complete? I mean, there is
Well, you have
there is a
to-
mathematical notation for it. It says
You have to say
it's not
something
it.
about what's happening in the discontinuous layer at the surface or some discontinuous vortex sheet somewhere. You have to
no.
add something to bring it
You need
the
to
real
add more
physics.
information. That's the selection criterion I'm talking about. So this is very well known in the math community. It's not my stuff. So in the math
But,
community,
No, I'm not saying it's your stuff or anyone's stuff. All I'm saying is that a weak Euler by itself doesn't answer the questions. You have to
And I'm
say
saying-
something more about vorticity generation.
it's
and-
not
and
vorticity
dissipation.
generation. It's a selection mechanism to select among the
Well, if you want circulation,
infinitely
you need
many.
You need
Doesn't have to be
vorticity.
circulation. No, it's not the old stuff. It's not the old debate. It's the issue is much bigger than this in the math community.
If you go beyond the question of an airfoil, yes.
Yeah, and you can project it. You can project it on the airfoil. The point is, there are infinitely many Euler solutions, and that's, in my opinion, the $1 million question: how to pick from this infinitely many, the family, the unique solution that matches the implicit limit of Navier-Stokes. So we have two ways, Bill. We have two ways. If we have the luxury enough to keep solving Navier-Stokes as at a sequence of vanishingly small viscosity. Like I take viscosity 1.1, 10 to the negative 6, 10 to the negative 20. Hopefully, I'm converging to a limit, right? I reach that limit by solving the purely viscous problem at each step, right? Alternatively, we know that limit lies here in the family of Euler. How can we pick it up? That's the $1 million question. Why it's $1 million question? Because it will allow industry to go and simulate Euler. It's very cheap, use this selection mechanism, and we don't need to resolve boundary layer. So this selection criterion is not there yet, and this is why in our group we're obsessed with the minimum pressure gradient. We feel like, or any minimization criterion, like I discussed with you before, we feel like we need a selection criterion. That will be very useful. But yeah, go ahead, please.
Sorry, no, for the boundary condition, still non-penetration.
For Euler, that's
nothing special.
Yeah, that's the interesting point. Yes. But from a numerical perspective, now this is pure mathematics. Now let's go to a numerical perspective. If you simulate Navier-Stokes at a large grid size, LES, you need a subgrid scale model. And there is no subgrid scale model that comes from first principles. Everyone comes up with a reasonable model. You assume a model for the subgrid scale, right? For the Reynolds stress. In the same token, use the same subgrid scale model with Euler. Of course, we're talking about very high Reynolds number. If you use it with Euler, it will give you a very reasonable flow field. That's the story that they are telling.
Yeah.
So from a numerical perspective, the issue is similar to Navier-Stokes and Euler. Now, what we need a good model for the Reynolds stress. For either, it does not matter now. Okay? From a numerical perspective. Xian, please.
Hi, so if there's multiple solutions for Euler equations, then how do you guarantee that if you keep decreasing the velocity, viscosity of Navier-Stokes, then it will converge to the correct solution? Why wouldn't it go to a different solution?
That's an excellent question, and it's an open problem in mathematics, which means there is no general proof that says that for every single case we will converge to a solution of Euler. maybe in 10 years from now, someone will come up with a counterexample, but it also means that there is no single counterexample to date that this was not the case. All right? So this is why Greg Eigen was saying, under modest assumptions, you expect convergence. And the issue, by the way, go ahead, Shyam, please.
Just another related question is that if there is a naturally selected Euler solution, and we know that for steady state there's multiple unique solutions, can we think about how do you advance the unsteady solution from a given initial condition that will give you the right Euler solution? I suppose the argument you're making is that at steady state you have many different weak solutions satisfying the Euler solution, right? But how do you
But
think
that's an excellent point. There are 2 points here I'd like to make. Unfortunately, the non-uniqueness is not only in the steady case. The non-uniqueness is also, okay, let me paraphrase this. In the steady case, the situation is more problematic. Why? Because there is non-uniqueness even in the space of smooth solutions. Even in the space of smooth solutions, we have non-uniqueness, and this is why we managed to play a role, whether it's, it was an interesting role to pick up from this smooth solutions. But now for unsteadiness, we know that you're gonna have a starting vortex. You're gonna have a vortex sheet, which will roll up into a starting vortex, and this vortex sheet is discontinuous. So if you wanna capture a physical transient response, it would be weak solution. Now, in the realm of weak solutions, even unsteady, they are non-unique. You can develop however you like. That's an issue. So you need a selection criterion even to pick up the right transient.
So even for common advancing, you did
Yeah.
You did some sort of criteria.
Yes. So this is the point. So now let this on aside. Going back to the steady case or whatever, I think a natural mechanism to pick the steady. Look at the stability. Nature will select the stable solution. The unstable solution, you will never see it in reality. So I'm wondering why this has not been done. It's for the airfoil problem, why we did not do a formal stability analysis of the infinitely many possible equilibria of Euler, one with zero circulation and one with Kuttas and blah blah blah. My guess is that it's a non-trivial stability problem. You need a nonlinear stability criteria. It's not a linear stability criteria. It's something like when you go check all the eigenvalues are in the imaginary axis, kind of. So it's not. You need a nonlinear stability theory. So one point I want to make related to, because some people think, why bother? I mean, Euler with too many weak solutions and selection. We're happy with Navier-Stokes. Let's stick with Navier-Stokes. There are similar issues because Navier-Stokes compressible is known to develop singularities in finite time. And if they develop singularities, then how to advance beyond the singularity time? Well, you have to understand it as weak solution. And again, for Navier-Stokes itself, with viscosity and no slip boundary condition, once you open the space for weak solutions, it's non-unique and you need a selection criteria. So it's the same issue. Any question? Please.
Is it known that incompressible Navier-Stokes doesn't have discontinuities in finite?
That's an excellent point. 2D, yes, we have Lady Zinskaya, the Russian lady, proved already global existence for Navier-Stokes, so that's okay. But for 3D incompressible, we don't know. It's an open. That's precisely the Millennium Prize problem. And since we don't know yet, we may have singularities, so we have to speak this language of weak solutions. And for the compressible case, we know that it develops singularities for finite time, so we have to speak this language, unfortunately. Yeah. So let's say if someone proved this Millennium Prize problem, that Navier-Stokes have global solutions that do not develop singularities in finite time in 3D, then we can, with good conscience, simulate Navier-Stokes incompressible perfectly fine without need to know about this language of weak solutions. But so far we cannot. And for the compressible case, we cannot. Please, Mark.
What's the justification for having the velocity distribution be an L2 function?
The justification?
Yeah, why does it have to be in L2? Like, basically you're requiring that the holder exponent would be greater than 0.
Yeah.
Why not negative holder exponent?
No, I don't think they require that the exponent to be greater than 0.
No, because then you'll get infinities. Because if you have a negative holder exponent, then like as you take the limit that or any integral.
So what kind of
one over x situation?
What kind of space are you thinking about if it's not L2? What kind of space?
Well, I mean, I don't know. Just L2 is a restriction. So
because there is some subtlety here. So if you take a velocity field with circulation, it's very simple stuff. Gamma over 2 pi r. This is not L2. So there is difference between L2 and L2. So I don't think that this is what you're talking about. Like this simple flow field, gamma over 2 pi r, is not L2. So in this sense, there is remedy. I mean, I'm sorry. In this sense, not being L2, you need to account for these kind of flows. And they can. So that's okay. They do some sort of modifications and blah, blah. I think what you're describing is something different. You're describing is a singularity in the flow field, and very strong singularity.
Yes.
And it's not in the derivative, it's actually in the velocity itself. So it's not defined at some points in the domain, right? Is that what you're saying?
Like any smooth, well-bounded test function wouldn't give you a finite answer if you integrate over the velocity field.
Yeah.
Like you earlier you said that like we need to open up instead of just considering real solutions to some algebraic equation, you include imaginary.
Yes, exactly.
And
exactly.
why not include more? Like why only L2 then?
I'm not sure if they are restricting themselves to L2, frankly speaking. That's I'm not sure of. But I know that in these convergence theorems, most of them, the convergence happens in L2. I'm not sure if they're doing this confinement. But the issue is, even with this confinement, the mathematicians could not answer the question. So I don't think it makes sense now to go and try to solve a harder problem. I don't know. And remember, when they think of this, mathematicians, math analysts, they're trying to open the space until they manage to prove existence. Once they prove existence, so it's okay. So they are sure that the solutions that they are looking for in that space. This problem, by the way, is taking the minds of the best mathematicians of the time. This is far from being true. In fact, these papers, I don't think that we are preparing our fluid mechanics students to be able to read these papers. They are very difficult. They were very difficult for myself. So, but the issue, what I'm struggling with, is that they are very difficult. But do I have the luxury to ignore? And the answer is no, because they are relevant. So that's the point. If there are no questions, I promise. Yeah, Shian.
I guess I'm asking another.
No, please.
Question. I mean, I also do simulations with more rectangle simulations, right? And I worry after learning about all you're presenting today here about what I'm even doing, right? Like, why do I trust simulation to begin with whatsoever? So I guess, are you implying that when it comes to scenarios where you have singularities and discontinuities, it's a lot more possible that your solution may actually giving you very different results compared to, for example, external measurements, because the current equation construct doesn't capture the impact introduced by.
I mean, short answer is yes. I mean, if you are not building, you know that there is finite volume, there is finite difference, and there is finite element, and there are some versions of the finite element that they really take care of these. They build the code around the expectation that they can capture a weak solution. So it depends really on how you build your code. If maybe 15 years ago, if I'm building a code, I'm not aware of these kind of things, and I'm building the code just directly. I may not capture the most physical solution. It can happen. If there are no questions, I promise that this is the last part. because I promised this last time.
Conclusion.
Come on.
Oh yeah, there is no. I didn't give a conclusion. Well, there is no conclusion really. There is just acknowledgement to my group and the funding agencies, and that's it. So